All right then. So electricity, everyone's favorite topic. And I should change my pen color again because it likes to go to red. So we have electrical parameters. First things first, we're talking about charge, the element of electrical energy transport, or in coulombs. That's the measurement is in coulombs. Current is in amperes, the rate of flow of charge. All right, 1 amp is equal to 1 coulomb per second. You have voltage, it's a potential. All right, it's otherwise known as volts. It's the energy per charge gained or lost. 1 volt is equal to 1 joule per coulomb. And then you have power, which is in watts. It's the rate of electrical energy production, transmission, or consumption. And then you have resistance, R, or the sigma, which is ohms. All right, the opposite of the opposition to charge. Flow measured as the ratio of voltage to current. And then you have your 3 equations right there. R is equal to V over I is equal to V over R, and V is equal to I over R. And that is 3 ways to write the same equation. All right, later in this class, we'll get into how to memorize those easily. So first thing, we have charge. Charge comes in packets of coulombs. All right, either positive or negative. Opposite charges attract. Like charges repel. All right, 1 electron is equal to negative 1.602 times 10 to the negative 19 coulombs. All right, 1 negative coulomb is equal to 6.24 times 10 to the 18 electrons. All right, this number comes up a lot in your engineering fields, like a surprising amount. So that's 6.25 million trillion electrons is equal to 1 negative coulomb. Again, guys, I'm going to post these slides right after class, even though there's 39 of them, all right? So current, you have the actual electron flow. This is the way electrons will actually flow in a wire, all right? But this is how we read conventional current and how we represent conventional current. All right, the number of coulombs, positive or negative, passing any point in 1 second is current in amperes. All right, so it's any 1 point. So their measurement is a reference point of right here. All right, so if you were to take a look and you had a voltmeter and an ammeter, all right, and if you wanted to take a measurement off of a light bulb, the only way to actually take that measurement would be to put the amp meter right here in line. All right, an amp meter has to be in line because it's taking a measurement through a singular point. So it has to go through the amp meter. All right, whereas a voltmeter can be taken between 2 points. All right, a good way to remember that is you have the symbol for volts is V and the symbol for amps is A. All right, the good way to remember an amp meter needing to be at a singular point or through the amp meter is that the A, when written capital, has a line going through it. All right, so if you write the anarchy A, you have a line that goes through the A, is what an actual amp meter needs to take its reading, where voltage does not. All right. So voltage is the energy in joules gained, positive or lost, by a column of charge moving from point A to point B. Voltage is measured between 2 points. At a point, like current, is a comparison of potential. All right, we're comparing point B to point A and point A to point B. All right, so we would take a voltmeter and stick it between these 2 points. You would take your 2 leads and you'd put it on opposite sides of what is being read. But the current is not traveling through it. If you were to have an amp meter, it would go right here. All right, so a 12-volt battery is equal to 1 volt is equal to 1 joule per column. All right, so you would have basically a 12 joule. So a 12-volt battery is equal to 12 joules per column. All right, so each column gains 12 joules through the battery. And each column gives up 12 joules through the bulb. So everyone remembers when I was talking about refrigeration and how I did not like the comparison from refrigeration to a motor and piping system, where I thought it was not a very good comparison. It more confused people than helped you out. Whereas with electricity, this is a very good way to think about it. All right, because you can't see electricity. You can only take readings. You can see it, but that's when it gets bad. But this is a good comparison. All right, so voltage is similar to the energy in pounds per inch gained or lost by a cubic inch of liquid moving from point A to point B in a piping system. All right, 12. So if we have a 12 psi pump on one side, where 1 psi is equal to 1 pounds per inch over inch cubed. All right, we have a valve over here causing a restriction. That's just like our light bulb. All right, and over here is just like our battery. And that's something I should point out to you guys. By the way, this is a new symbol that we just learned as well. This is a symbol for a battery. All right, the other ways that you can see it would be, more often than not, it looks like that. You won't have so many layers of it. Usually the symbol is just 2 straight lines with 2 straight smaller lines in between. That's the normal way you would view these things. All right. So we have a restriction in flow by this valve. So voltage is not equal to pressure. All right. What we're saying here is that voltage is the pressure. All right, just like those SAT words right there. So voltage is the pressure as current is the fluid flow. They're not equal, but they're a good way to think of each other. All right, voltage is our pressure that we have in a system, where current is our fluid flow, and gallons per minute is our coulombs per second. All right, our voltage, which is joules per coulomb, is pressure, which is pounds inch per inch cubed. So each inch cube gains 12 pounds inch through the pump. So each inch cube that goes through this pump is going to gain 12 pounds inch. All right. And then each cubic inch that goes through this valve, through this restriction, gives up 12 pounds inch of force. All right. And what we're measuring with voltage is between these 2 points, our differential between these 2 points. We're comparing A to B and B to A. So power is the rate at which energy is delivered to a fluid is pressure times flow. In English units, it's PSI times gallons per minute over 1714. That's equal to horsepower. In SI units, it's newtons over meters squared times meters cubes per second. That's equal to Newton meters per second. And that's equals to joules per second. And joules per second equals watts. So let's move on to power. The power is the rate at which energy is delivered to or retrieved from charges is voltage times current, which is pressure times flow. So joules over coulomb is equal to volts. All right, so we have volts times amps is equal to watts. Or we have joules per coulomb times coulomb per second is equal to joules per second. All right, so 12 times 1 watt supplied. So 12 volts times 1 watts, which is our amps. I'm sorry, 1 times 1 is given our watts. All right. So as we go through and we have power, in most power systems, the voltage is constant. We talk about a 12 volt battery, or if you have a 24 volt battery, or you have a 124 volt system, which is a house voltage. All right. The number and types of loads turned on determine the current and power. So right now we're sitting here with a 120 volt source. We have no current and we have no power because we have nothing going to anything. It's just sitting here. All right, but that all changes as soon as we start to add. All right, we have a 60 watt consumption here. All right, and through the equations that we learned earlier, we get 0.5 of an amp coming out. All right, so the next we add is a 240 watt. And then we add 180 watts. So what we do here is we have a 120 volt source. We add up all of our watts, and then we add up all of our watts supplied. So the more items we turn on, the more power we draw. The longer we let things run, the more energy we consume. So energy is equal to power times time, which is watts times second is equal to joules. So this is how you actually get billed. If you were to pull your electrical bill, this is where you actually get billed for. That's how you get money out of basically your energy consumption. You're billed in energy consumption in basically dollars per kilowatt hour. The way they get that rate is basically their own equation. All right, how much it costs to produce that amount of energy. All right, and then they want to make a profit, so then they have to have a little bit of a profit, so then they bring it up a little bit. All right. So what you use will be in kilowatt hours. So if you used 100 kilowatt hours of energy, all right, and basically if it was $1 per kilowatt hour, simple math says that it will basically be $100. All right, that's how your bill is oriented. All right, and that's how you get billed with everything that speaks about kilowatt hours. How much it costs per kilowatt hour. Any questions so far? All right. So what determines how much current a given customer will draw? It's resistance. All right. So if you have a 120 volt, 60 watt bulb, it draws a half an ampere. So basically you have 120 volts times 0.5 an amp is equal to 60 watts. Because it has a resistance of 240 ohms. The higher the resistance to the movement of charges, the less current through the device. A bulb with a 360 ohm filament, remember we're talking filaments, those are the old style incandescent, not LEDs, draws only 120 over 360, 1/3 of an amp, and consumes only 120 times 1/3 of an amp, 40 watts. All right, it has a resistance to flow. It resists the flow of electrons. So, like we talked about, we have an easy way to remember our relationship between power, voltage, current, resistance. All right. You have these two diagrams. You have PVI and you have your VIR. These will just have to be straight memorized. But it helps you to remember all of your other equations. All right. If you want power, you put your hand over power, and now you have V times I, or your voltage times your current is equal to power. All right. If you want your current, you put your hand over current, and now you have your power over your voltage is equal to your current. And the same thing goes with your voltage, current, and resistance. All right. If you want current again, put your hand over it, and you now have voltage over resistance is equal to your current. All right. And as we go through, here's just some good examples of what we have. All right, so there's just some math equations that you can be doing for practice and check yourself. Whoa, went through way too many slides. All right. So as we go through, we have direct current, all right, or DC current. DC basically means constant, all right? It's a constant flow. It flows only in one direction. The DC voltage remains at a near constant level. So voltage sources, you got batteries, you have DC generators, and you have rectifiers, all right? Rectifiers are electronic circuits which convert AC power to DC. So rectifiers with an additional voltage regulating circuitry are called regulated power supplies. DC voltage sources are analogous to, basically, they're just like centrifugal pumps. All right, that's the way you can think about them. Centrifugal pumps have a near constant pressure with flow determined by connected systems. It's the same thing with DC voltage. All right, the voltage is at a constant level, but your actual current is determined on what's connected. So let's talk about an automotive circuitry. All right. What we have, very simply, is we have an engine down here. We have an alternator. So this is our alternator. This is our engine. We have a pulley that's turning the alternator. We have our rectifier. We have our battery. And then we go through and we have spark plugs, headlamps, radio, signal turns, all that other good electrical stuff that we have. All right. So first things first, when we start up an engine, we have our key, and our key turns on our ignition. All right, that's represented right here. We use the battery's power. You start the vehicle, and we complete, give me a second. We complete the circuit, and now we have power goes to our spark plugs, and our engine turns on. All right. There we go. So, just looking at this, we have an alternator. It's spinning. It's creating a charge, and it goes through our rectifier. All right. What we're doing right now is we're charging our battery, and we're sending power out to our spark plugs. The engine is just running right now. All right. We close another switch, and we have headlamps. We turn on our radio, closes another switch, and we have our radio. All right. And then everything else that's electrical in the vehicle, this is how we're getting power. Our power is not coming from our battery. It's coming straight from our alternator. With knowing that little bit of information, what's the point of knowing this? How can you tell when an alternator is bad? What will happen to the vehicle? If you're just driving along and all of a sudden your alternator goes bad like that, what happens?
You're going to slow down.
So you're going to slow down, but what else? What will happen not right away, but what will happen quite quickly?
All the electricity will start.
Yeah, your battery will just drain out, so electricity is gonna.
It's just trying to run off of your battery, and then all of your external, your radio, your radio's gonna die first.
Because doesn't the alternator just like make sure that everything's running electricity-wise, So if your alternator goes bad, that means the battery's just continuing. It's just going to drain out.
Exactly. So your battery's not being recharged. So now your battery is supplying everything. All right. So first thing that would go out is your radio, right? Radio consumes a lot of electricity. And then your headlamps will start to dim, and then they eventually go out, and then your spark plugs will go. All right. So you will basically start to the car will begin to slow down. You will have huge issues with the vehicle, and it'll eventually just die and stop. All right. If you have a bad alternator. Now you will slow down because you'll having like every couple of times the piston comes up, it won't fire one time, and then it'll come up another time, and it might just have a little bit less resistance in that spark plug. So then maybe that one fires. So you basically will have, and eventually your car will stop if your alternator dies. So what if your alternator's fine, but you have a bad battery and your car is running? You're driving down the street. What happens? Nothing?
Basically. I mean, the battery would be dead, so you probably wouldn't be able to start it. But if you do get it started, you'd probably have everything would probably be fine.
What if you jump the car?
Exactly.
Yeah, we're just talking of the fact that if you're driving along, just like the alternator, if you click your finger and all of a sudden you could turn your alternator off. If we turned our battery off mid-drive, we already said it in the chat, but it was basically you would be fine. All right? Because your alternator is supplying enough electrical power. Just because your battery is bad, and you take it out of the equation, your spark plugs still have a route. All right? Your headlamps still have a route back to the rectifier. The rectifier is still getting a charge, so it's getting recharged and it's going out and sending power out. All right? So everything will be fine. But as soon as you turn that vehicle off and you kill this engine, you no longer have a source of power and you don't have an ability to start. The first animation we had was the power coming through our ignition and sending power to our spark plugs and starting up the engine. All right, so you would have to be jumped. All right, which is taking power from somewhere else and starting up your car. So that's how you can tell if you have an alternator that's the problem, or if you have a battery. Oh, someone entered the chat. All right. Now, let's talk about something else here. Actually, let's go into discard that, go to this, screen share that up. All right. So let's talk about shipboard batteries. Now, we talked about a car battery and how it's important for it to start up an engine, all right? Because it's going to start your starter, and your starter is electric. It's not air-powered or hydraulic-powered, all right? It's powered off your battery. Now, on ships, we have generators, all right? We have diesel generators. We have, on the TSES, we have turbo generators, all right? The turbo generators don't have backup batteries. So the diesel generator on the TSES has backup batteries, and most vessels that you go out on will have backup batteries. All right. These are run basic systems that are onto the generator to regulate it, all the electric systems to do the starter. But the starter itself is not electric. It's air powered or might be hydraulic. All right. But just know that these batteries are needed to start up the engine. They won't be directly starting it with an electric starter, but it will be sending out signals. So they're needed. So depending on the size of the generator, emergencies usually will have about 4 batteries each. All right. Just regular generators will have either 2, maybe 4. All right. 12-volt batteries. Now, these batteries are hooked up to a battery charger. All right. So you have a nice battery charger that's coming off of the generator. They go into a nice, basically a rectifier. All right. And they have wire terminals that come off and they go to the batteries. So every Sunday, on pretty much every vessel you go out on, a third's responsibility is to do battery checks. You just go and walk around with your voltmeter. Sundays are usually very nice days. It's like a no work day. Everyone's doing easy work, no projects. The deck side usually gives their ABs off. On some vessels I've been on where they just don't have to be in work, sometimes it's just watch standing. So you just sit in the control room, you sit on the bridge. Unfortunately, if you're offloading cargo or taking cargo on, you just don't have Sunday that day, that week. All right. But Sundays at sea, you go out, thirds usually go out and do their battery checks, which basically means you go out to all the batteries on board the vessel with a clipboard and a nice Excel sheet that you printed out, and you write down all the voltages that you get from all the batteries to check if they've gone bad. All right, because remember, if these go bad, we can't start our engines. So the first thing you do is your generators are running, right? Because you want to have power. So they're sending power to your rectifier. All right, which is getting a DC voltage. Now, in line, what you'll have is a switch. All right, and switches can come in really any kind of way. Sometimes they'll look just like a general switch, where it's basically just an up and down. It looks like a light switch on a nice big box. I couldn't find an image of it, but I do have other images that you have, and you will see on board a vessel. All right, so you have these red ones here that could just be on or off. Now these ones right here are the big ones that you'll see a lot of. 1, 2, 1, and 2. All right, and then still in off position. So that basically means you want to be charging battery 1, you put it to battery 1. Battery 2 is not charged. All right, same thing vice versa, or if you want both batteries to be charged. And then you have your off position. All right, so when you switch the share back to here. So when you go and do your battery check and you stick on a voltmeter, and you take your 2 voltmeter probes, you guys are back to the whiteboard, right? Mm-hmm. Okay, good. It doesn't tell me which one I'm on. And you go up to and take your voltmeter, you take your 2 probes and you stick it to your voltmeter, stick it to the battery. What should you do to the switch? What should you do to the generator, the rectifier, the battery itself? Should you spin around in a circle 3 times and spin on the floor before you put your voltmeter on? What should you do? What are you trying to read right now?
The battery.
You're trying to read the battery, right? So what should we do to the generator?
Switch it to another battery or turn it off.
Should you turn the generator off?
Turn it off.
Or you can switch it to another battery. I don't think it matters.
So remember, these are diesel generators, all right? So they don't need a battery to run. All right, this is for starting. So we're going to leave the generator online, all right, because the ship still needs power. We still need to operate. All right. So what do we do with the switch then?
Would you just like switch it so it's not a closed circuit, so that there's no flow going to the battery?
Exactly. And you use the right terms there. You won't have a closed circuit. All right. So you're going to open the switch. All right. You're either going to turn it to the off position, or you're just going to open the switch. And sometimes, like I said, you could just have a light switch that will go to both batteries. All right. We have these two wires that are going off, and it just leads to both batteries. And one switch controls both, or you can be in a position where it goes to 1 and 2. All right. Most ships I've been on, emergency generator rooms will have a switch, like we said, where it has an option of 1, 2, 1 or 2, or off. All right. And most times it's all switched to 1 and 2. All right. And then most generators will have basically a light switch. You turn it on or off. It's what's on, you're charging your batteries, or it's off, you're not charging your batteries. So, sorry guys. Generator's still running. All right. We open our switch, so now we don't have current going to our batteries. And now do we take both of our probes and we stick them right on and we just call it a day? We take that reading and just move on. We want to get done. What happens if we turn the battery off and we just take it right from a charging position? We open the switch and we take an instant reading right there and then. What would we get? What sort of reading would we be taking?
It'd be 24-volt reading.
Well, it won't be 24 volt because we're going to be taking a reading individually of each battery. All right, but think about it. It's not an automatic. All right, so we're going to still have like just a little bit of current that's going to be still there. All right, it's not like these switches when they're open is going to have like electricity still powering it through the midair. If you have that, that's a bigger problem. All right. But what you're going to have is just a little bit of like leftover current, or like it's going to be charged up. All right. So you're going to have not just 12 volts, but you might have, if it's a bad battery, it might be like 16, but you'd be running around 13 or so volts. If you take a charge, if you take the switch, click it off, you open up the switch and you take your power and you voltmeter it and you just go right in right away, you will get a higher than normal reading. All right, because you barely gave it any time to get it, so that way the battery and reading the actual battery, not what it was getting charged to. All right, so you just let it sit for like maybe 5 or so minutes, 5, 7, 10, 15 minutes, nothing longer than 15. Not that it will drain too low, but the problem is that you're trying to make sure you get a proper reading of the battery without draining it all the way. All right, so that's how you get a proper battery reading. You make sure you turn off your switch, you open the circuit, so you have no power going to it, because we're not trying to read what's coming from a rectifier or what our generator is producing. All right, we're trying to figure out if these batteries are bad or good. All right, most of the time you'll just get something like 1204 or 1213. Really, it's one of those things where you're going to see a battery stay fine, and then it'll be a slow death. All of a sudden, you'll have stuff where it will just, after weeks of taking readings, and when you're stuck on a boat for weeks, you'll see these things. It'll be, all of a sudden, it'll be 1200, and then it'll be 120, and then all of a sudden, as you start to go down, you start to see that dreaded 11. And then from there, it just goes. And once you hit about 10, you're dead. But it will stay up in the 12 region for a long time. And then over the course of about a month, you'll go from 11 to 10. But it'll stay years in this. So what happens if you have your red probe and you have a black probe on a voltmeter? All right. Red's usually positive. Black is usually your ground on a voltmeter. All right. So you take your positive lead and you put it onto the positive lead of the terminal. Take your negative ground and you put your negative ground onto the negative side. So what's your reading? What will you actually get? So say you have a 12 volt reading. Would it be positive or negative? Taking your red positive lead from your voltmeter and you stick it on the positive side of the battery. And you take your negative ground lead from your voltmeter and you stick it on the negative side of your battery. What sort of reading will come up on your voltmeter?
Positive.
You'll get a positive reading. All right. What happens if you reverse it? You go red to black, black to red. Does your voltmeter blow up in your hand? What does the voltmeter show then?
Negative.
It's just the straight negative. All right. There's nothing wrong with just going the opposite direction as far as when you're reading voltages. It's good practice to stay red to positive, black to negative. All right. But all you're really going to get is just a negative 12 volts. Whoa. All right. It will be the same reading, but just in the negative, because what you're going to be reading is the comparison between these two. Remember, it's the potential. All right. Anybody confused on any of this as I drag it around the screen? All right. So we're going to go back to the PowerPoint. And share this. Okay. So here's the other question. If we're on a diesel engine, diesel car engine, and we destroy our alternator, what happens? Does the car stop?
You still have the battery running.
Will it stop a bit? Will it stop eventually?
Yeah.
No, because it's a diesel.
What happens
Yeah,
in a diesel?
They don't have spark plugs.
Yeah, they don't. Yeah, exactly.
Okay.
So a diesel engine doesn't have spark plugs. All right. So keep that in mind when you guys are going into diesel class and everything like that. But just remember why your car is going to be stopping. All right. A diesel engine works off the principles of compression and the heat of compression, all right, to ignite the fuel. Whereas with an actual gasoline engine, it's using a spark plug. Where a spark plug is actually going to be your ignition source. All right. It's like putting a flame to a candle. All right. Whereas instead of putting a flame to a candle, we're using a little piece, we're jumping two leads and we're getting a spark that's going between the two. We're using an electric source to go through the two. And as it goes through the two, fuel is in the air combined with air, and we have our ignition. Where in a diesel, what we have is a volume of air compressed. It heats up because it's compressed, And at the top most of its heated and compression cycle, we're basically going to atomize fuel and it gets squirted into it and it explodes and we have a power stroke. All right. So basically for the quiz for Wednesday, we're going to go all the way up to this slide 15. All right. But we're also going to include what I'm going to talk about after this. But this is for the slideshow. All right. So on the TSES, we have a nice little system called the general alarm, which you're all going to become very familiar with, especially when you're in the middle of your sleep. All right. We have ship's AC power coming in. It goes through a rectifier, and now we're on a DC current. All right. Now, we have 3 positions where we can open or close switches to initiate our general alarm. Right now, this one is closed. We have current that allows us to go through our general alarm. Now, we have 4 batteries that back up our ship's power. Because most of the time, if we have our general alarm going off, unless it's an actual drill, we're going to need our backup power to signal it. So in this configuration that we have right here, the ship's power is coming in, all right? Comes out and goes to 2 places. It's either charging our batteries or it's going in this direction. All right, and if this switch is open, and I keep saying open because the switch being open means there's going to be no ability for the current to flow through, we're going to be charging our batteries. But if this switch closes, we're still going to be charging our batteries. We're just going to be having a general alarm going off at the same time. Now, if we lose ship's power, instead of the ship's power charging these batteries, we now have these batteries sending out a voltage. But if none of the switches are open, as none of the switches are closed, they're all in the open position, we're not going to have any general alarm. As soon as one of them closes, we have a general alarm. So, discard those. Yeah. This thing likes to yell at me. Let's go to the whiteboard. And let's go over here. All right. A couple of terms right there that we need to hit on. We have open and closed. All right, right here, that is in the open position for a switch. And that is the closed position of a switch. All right, along the same lines, these are both a symbol, just like this is the symbol for a battery. This is the symbol for a switch. You can have different variations of that, but this is basically what you're going to see as a switch, or it could even just be a line that comes straight up like this. I just like this variation better because this at least tells you there is a switch there. All right, sometimes it might even have a little bit of, like, they're called nodes. That'll look like that. All right. So that's an open switch. And that's a closed switch. So no flow of electricity or electrons. And this says yes, current. Yes to flow. So the main thing you have to get straight in your head is how an open switch has no current flowing through it. A closed switch has current flowing in it. All right? Whereas with valves, an open valve has flow. Whereas a closed valve, what's up?
Are you going to be posting these things on Blackboard too? These little things you drew?
Not. Maybe if it's something like simple like this, then yes. I'll take a picture of it and go from there. All right. So, whereas if we have a closed switch, then we're not going to closed valve. Sorry, we're not going to have flow. All right. They're opposite of each other. The electric and the mechanical version are very opposite of each other with this terminology. So an open valve, it's open. It has flow going through it. But an open switch, it's open. There's space in between it. It's an open air. All right. There's no current that's going to be going through that switch. An open breaker, a closed breaker. All right. Closed breaker has current going through it. A closed valve is a physical barrier. It's stopping it. All right. So make sure you just have those two things straight in your head as you go through. All right. If you're having trouble remembering, you're all at home. Go through when you turn on the light switch. Instead of saying turn on the light switch, say you're closing the circuit. All right. If you're opening a valve, instead of turning on the faucet, you're opening the valve for the faucet. All right. Just say those into yourself when you're in your own head, because you'll sound crazy to the rest of your family. All right. Just say it out loud to yourself if you're confused by it. All right. Write them on. Don't write them on the wall, but post a little thing on the light switch to help you remember these things. All right. But this is something that you're going to hear all the time and you want to keep straight. So let's talk about something else here. We have two things called a parallel circuit and a series. P-A-R-A-L-E. So with a series circuit, you basically, I'm just going to use resistors. We're just going to say that they're light bulbs. All right. Just because I don't want to draw a bulb every single time. All right. We have light bulb 1. We have light bulb 2. And we have light bulb 3. So with a parallel circuit, we have something like this. Each light bulb that goes through has their own path for flow, for current. All right. And that's the important thing to differentiate. So if you were to turn on this circuit, you were to close this circuit to power, both of them, and then walk away, and you come back in 5 minutes, and one bulb is out. Say light bulb 2 is out on both circuits. When you come back into the room, and you still have a closed circuit, what is happening on the parallel and what is happening on the series? What is bulb 1 through 3 doing on both circuits?
On the parallel one, 1 and 3 are still on.
Yep.
But in the normal series, light 3 is off, light 1 is still on, it's still receiving power.
Still receiving power, but where?
Oh, but it's not a completed circuit, so it would still be off because the power has nowhere to go.
Yes. So what we have right now is with the power. So if light bulb 2 is out, all right, bulb 1 and bulb 3 are still on. They're still lit. All right. Where bulb 2 is out. All right. But in the series, bulbs 1, 2, and 3 are all out. All right. Just because bulb 2 is out. All right. There's no way for the current to continue. It goes through light 1, great, but it can't complete the circuit. So there's no way for the power to return, to gain more energy, and to continue on. All right. Where with the parallel, we have the ability for 1 to have a completed circuit. Well, 2 comes along, and now it's broken. But 3 continues, and it has a completed circuit. Everyone see that? Okay, good. Now this is why people hate old Christmas tree lights. Because the older lights are in series. When you see people and they have one bulb that goes out and they have no idea which bulb it is because it's a series light bulbs. All right. But everyone's buying these new light strings because they're all in parallel. So then why, if one bulb goes out in these new light Christmas tree light series that we have, why does one section of like 5 bulbs go out? Why is that?
Well, was it like a parallel series where instead of just having one bulb on one of the like outlets, you have like 5?
5 in what? In what configuration?
So instead of like in the example you drew, the parallel, you have 1, 2, and 3 on their own separate lines.
Mm-hmm.
But maybe with the Christmas lights you're talking about, you have 5 lights on one.
So on like a series line, right?
Exactly.
So how I'm drawing right now?
Side of a parallel.
All right. So that's exactly right. So you would have something that looks like this. And 3 is good enough. So you have lights 1, 2, 3, and 4 over here. And the craftsman got lazy, so he only did 3 on the other one. All right. So this is like a series parallel. All right. So bulbs 1, 2, 3, and 4 are in series. And then we're going to go 5, 6, 7. All right. And then we have 8, 9, 10 over here. All right. So each one of these series, bulbs 1 through 4 is their own series. Bulbs 5 through 7 is their own series. 8 through 10 is their own series. If one bulb goes out, if bulb 6 goes out, what happens?
Bulb 7 will go out.
Bulb 7 would go out, but what happens to bulb 5?
It also goes out because it can't complete it.
What happens to bulbs 1 through 4 and 8 through 10?
They're fine.
Hold up, one at a time. What's happening bulbs through 1 through 4 and 8 through 10?
They're still on.
They're all still on.
Yeah.
All right, because they still have their own ability to complete their circuit. All right. starting to like this whiteboard more I figure it out. So make sure you keep your open and closed straight in your head. You keep series and parallel straight in your head. All right. And as we get more and more into advanced things, keep that in your head straight. All right. Like I said, we're going to get into motor controllers and everything. It's good to be able to, just trying to find a good example. There we go. It's good to be able to sit there and use these base knowledge of your open and closed circuits, of what's happening between a parallel and a series circuit. All right, and when you start to add things and make it more complicated, like this one. All right. Keeping these basic concepts in your head straight will help you guys in the long run. All right, especially when it comes to electricity. So, like I said, quiz on Wednesdays, questions is slides 1 through 15. It's going to be 10 questions. The way it's going to be, the questions are going to be going, it's just going to be like question 1, whatever. And then right underneath, it's going to be question 2. All right, that's the style we're going to do. All right, same thing again. We're going to go over the quiz right after we take it. People have extended time. You're already in the system. So same thing, 15 minutes for everyone else, 23 minutes for everyone. You know, take your time. You guys do have a timer that sits on the above your quiz. All right, so study well. These slides are going to go up right after we're done talking. I'm going to post them to both classes. I'm going to be trying to continue posting these things to YouTube. Last Thursday, it just took me a while because basically YouTube crashed for the creator side. You couldn't upload anything. So I basically have to render these things and then submit them. All right, so I've been trying to get them up the day of. Sometimes it just doesn't work. That's the other thing. When you guys email me, tell me if you're in section 1 or section 2, all right? Or just do it easy, like 10 a.m., 11:30, just write in the subject line. So if you're asking me about grades or what's happening in the class or anything else like that, I can quickly get onto the Blackboard section and pull up your information and not have to open up one and then open up the other. It just makes my life a little easier. All right. Other than that, class is pretty much done for the day. All right. If anybody has any questions, I'll stick around for a few minutes. All right. Other than that, you guys good?
Test 3, is that
Yeah.
gonna be on, that's gonna be on electricity and hydraulics?
Yes,
And that's all, or is there anything else?
that's it. Anything else, or you good?
Yeah, that was it. I just want to
Okay.
make sure.
Everyone else good? So I'm going to close out the meeting. All right.